Okay, welcome to INQA seminar. Today we have a talk on exploring summary-like distributions in the quantum approximate optimization algorithms by Pablo Diez-Valle from CSIC. So Pablo, please.
Okay. Well, thank you, Tadase. And well, thank you first of all for the invitation, for giving me the opportunity to talk to you about a bit the work that we are doing on this interesting algorithm that is called the quantum approximate optimization algorithm. And this work is based on these two manuscripts. And well, hopefully we will publish another one on this topic on arXiv very soon. So, well, I'm going to start giving an introduction, okay, to be on the same page. The quantum approximate optimization algorithm, QAOA, is a hybrid algorithm that was proposed in 2014 to solve combinatorial optimization problems. This is the original paper, which is on arXiv. It hasn't been published in any journal, but it's very popular. And in fact, its popularity is increasing every year, as we can see in the citations per year metric. Well, we know what the meaning of combinatorial optimization problems. Those problems are those in which we have a discrete set of possible solutions so that we can encode every possible solution with a string of binary variables of bits. And the goal is to find the lowest energy state. There are a lot of practical applications for combinatorial optimization problems, and there's uncertainty about whether quantum computing will be able to find advantage over the very good classical algorithms that we have in this field. But it's true that any kind of small advantage in this field could have a huge practical and scientific value. QAOA belongs to the class of variational quantum algorithms. These algorithms are one of the leading strategies to find applications in these computers because we use a hybrid approach in which we combine classical computers with quantum computers to reduce a lot the number of gates that we need in the quantum part so that we reduce the noise. This is the general scheme of how they work. This picture is from this great review. We have an ansatz that is a quantum circuit that depends on several parameters, theta. And we have a cost function that encodes our problem. So we update these parameters using this loop, using the classical computer, and using the values of these cost functions, so that we update these parameters, and at the end, we make the answer closer to the solution that we want, depending on the specific problem that we are solving. In QAOA, we have these two main ingredients. We have an objective function, an operator that is encoding our problem. We have a missing operator, and that is not diagonal in the computational basis. So it allows the states to interfere between them, and hopefully it will amplify the amplitude of the ground state. And we can build the gate unitary operators from these two operators using two angles, variational angles, and variational parameters that are the parameters that we are going to tune. So this is the summary of the algorithm. We start with an initial state in which all states have the same probability amplitude. So we are in the full superposition state. And we apply these two operators on these initial states, intercalating them. So we intercalate them p times. You may visualize the algorithm better in this sequence, in this example with 5 qubits. We intercalate the operators p times, where p is the number of layers. If we increase p, we are increasing the accuracy of the algorithm, but of course we are also increasing the number of angles that we have to optimize, and we are increasing the noise in the quantum circuit. So finding the best p in a practical application is not trivial at all. And we can see how at the end, we have to optimize two P parameters regardless of the size of the system, which is quite good. And we optimize these parameters, minimizing the expectation value of the cost function of our problem. And why do we like this ansatz? Well, what's interesting feature of this ansatz is that it can be understood as a trotterized adiabatic quantum evolution. So in an adiabatic quantum evolution, we know that if we start in the ground state of a simple Hamiltonian, and we evolve the system adiabatically very slowly to a complex Hamiltonian, we can reach the ground state of this complex Hamiltonian. In QAOA, instead of having this slow evolution, we have an approximation with only P steps. So when we increase P, the number of layers, we are getting closer to this adiabatic quantum evolution. And when P goes to infinity, we achieve the ground state of the complex system. I said that QAOA was introduced for optimization problems, but here in this work, we are going to see the algorithm from a different point of view, a sampling point of view. So I think that it's important first to recall what's the difference between optimization and sampling. Okay. As I said, in optimization, the goal is to find the lowest energy state of the system. In sampling, we want to obtain several strings of variables which are sampled according to a specific probability distribution. Okay. So for example, in this case, if we have this quantum state in a quantum computer and we measure it at the end, what we are obtaining are strings of variables in the computational basis. And we are obtaining those strings according to a specific probability distribution that is defined by the quantum state. If we wanted to simulate the measurements of this quantum state in a classical computer, what we have to do is to sample those strings with that specific probability distribution that is defined by the quantum state. So in other words, in optimization, we are only interested in amplifying the probability amplitude of the ground state of the system. But in sampling, we are interested in the probability distribution of all the energy spectrum. We want to reproduce the probability amplitude of every agent state, of every point of the energy spectrum, to be able to sample these agent states with the specific probability. Optimization is very hard, but sampling is maybe harder. That's why sampling is a very valuable computational task. And in fact, there are some interesting works regarding sampling. For example, we have early demonstrations on quantum supremacy. This is the paper, the work done by Google. And I would like to highlight this work by Farry and Harrow, in which they demonstrated, using reasonable complexity assumptions, that the probability output, the output probability distribution of a QAOA cannot be sampled by classical computers, because otherwise the polynomial hierarchy would collapse. This is very interesting because it looks at the QAOA from a different point of view, but it's true that it doesn't give any clue about the specific probability distribution that this QAOA creating, and it doesn't answer whether we could use this probability distribution for some kind of application beyond optimization. And in specific, sampling Borman distributions or deep distributions, thermal distributions of Ising models is very interesting because at low temperatures, it's very hard to do. Low temperatures means high beta in this formula, the probability distribution. And it also has a huge impact on a wide range of fields, such as statistical mechanics, machine learning, combinatorial optimization. So at this point, now I'm going to dive into our work, in which we wonder ourselves, what is the nature of these quantum states produced by QAOA? What is the nature of this probability distribution that is hard to sample according to previous work? What is the physics that we can see behind these states? Can we learn something about the quantum dynamics of the dynamics of the quantum computer watching to these states? So let's see it. And to explain the work, I'm going to start introducing again the algorithm, but now I'm going to give a different picture of the algorithm. I'm going to picture the algorithm as an interferometry in the energy space. And I'm going to focus in the simplest version of the algorithm. So I'm going just to focus on one layer of the algorithm when P is equal to 1. And we can see how the algorithm is the same that applying a mirror at the beginning, with which we make that every AN state have the same probability amplitude. Then we apply the phase operator so that we split the branches of the interferometer, and we apply a different phase to every AN state of the system, X. The phase will depend on the specific angle, but it will depend also on the energy of the specific AN state. And at the end, we apply the missing operators so that we recombine the branches and we transport the phases into amplitudes that we can measure. So of course, this amplitude will depend on the specific phase that we are applying and on the missing angle. And hopefully this amplitude will be very high for the ground state of the system. We can understand this effect looking at this two-level system. The system in which we have two levels with this gap, sigma set is +1 and -1. So this is the expression of the probability amplitude for these two states when we are applying only one layer of the algorithm. And we can see in this plot how for optimal angles, after applying only one layer of the algorithm, we get full amplifications of either the high energy state or the ground state, depending on the angles that we are using. We can see it in the multi-level system also. We can see how the energy spectrum is transformed by QAOA. Here we are going to increase the phase angle, gamma, and we can see how the energy spectrum evolves. So we are increasing the evolution time of the Hamiltonian here. Now we start in 0, and we see how the energy, the probability amplitude, is concentrated at the middle of the spectrum. This is because of the spin model that we are using, and we have more density of states in the middle of the spectrum. That's why we have this shape. And now we start to increase the phase angle, and we see how the algorithm is shifting the energy spectrum to the left or to the right, depending if we are maximizing or minimizing. This is the same. We are just flipping the sign of the Hamiltonian. So we can see, for example, to the yellow line, and we see how we are shifting the energy spectrum to the extreme of the spectrum. We are amplifying the probability amplitude of the lowest energy states. When we reach an optimal gamma, we reach the maximum displacement of the spectrum, and spectrum start coming back to the middle again, to the initial state. This is nice, but it's even more interesting if we divide by the density of states. Okay, if we divide by the density of states, at the beginning we have the red line. Okay, so we have the same probability amplitude for all the energies because we are dividing by the density of states. And as we increase gamma and we increase the evolution of the Hamiltonian, we see how appears an exponential behavior at the extreme of the spectrum, so that the probability amplitude of the ground state is the highest. When we reach the optimal gamma, again, the probability amplitude of the ground state starts to decrease again. The system becomes more chaotic, and we lose that advantage that we were getting. So we thought that this exponential behavior at the extreme of the spectrum was very interesting. So we decided to explore it better. And we did some numerical experiments. In specific, we used different random instances of optimization problems, and we optimized the QAOA angles gamma theta for this specific problem, this specific Hamiltonians, minimizing the expectation value of that Hamiltonian. And then we studied the nature of this state that we have at the end of the QAOA circuit with optimal angles. So we studied the state vector of this quantum state. We studied the 2 to the n elements of this state vector, because we are studying the smallest enough problem so that we have access to the whole wave function. So this is what we want to see, what is the nature of this state. And for doing that and to increase the universality of the result, we explored different random spin models. In specific, we studied a Muscat model, a QAOA model, a random Ising. In general, they all can be described by an Ising Hamiltonian, as you can see, but they have different features. For example, in Muscat, we don't have a magnetic field, H. We only have the interaction matrix. So we have a parity symmetry. If we flip all the spins, the energy is the same. However, in QAOA, the symmetry is broken because we have this magnetic field. And we also explored different kind of graphs. These graphs define the non-zero elements of the interaction matrix J. So it defines the geometry of the interactions. We studied some random graphs, some regular graphs. In general, we obtained the same conclusions for all the graphs and models that we studied. So I'm going to present you the results that we got. Let's look first at the left column. Okay, here we are plotting the probability amplitude versus the energy. Each point corresponds to one AN state of the system with one energy, and the color tells us about the density of states, which is concentrated in the middle of the spectrum. And we see how this wave function fluctuates around the straight line that could be the Boltzmann distribution. Okay. So this is what we call Pseudo-Boltzmann states. This is just one random instance of different spin models, but we also average over many replicas. This is the right column. Here, to compare different random instances, one normalized the energy between 0 and 1, and we split the interval in 100 subinterval, and average over many replicas, over 1,000 replicas. Okay, and we can see how when we average, these fluctuations canceled between themselves, so that they are some kind of Gaussian fluctuations, and the overall distribution is very well described by this Boltzmann distribution. So our conclusion here is that QAOA is created poor but thermal-like states, or disk-like states, because it's creating a probability distribution that can be well described by a thermal distribution with an inverse temperature beta. Here, this temperature is obtained by fitting and this probability distribution to the thermal distribution. So we thought that this was very interesting, and we decided to look closer to the evolution of this temperature beta with the QAOA angles. Here we are fixing theta and varying gamma. Here we are fixing gamma, varying theta. And we see how the temperature is controlled by these QAOA angles and the size of the system. In specific, I think that it's interesting to look at the evolution of beta with gamma, because we see this interesting shape that is similar to a roller coaster, because we see how in the regime in which gamma is small, we see how beta grows linearly with gamma until it reaches a maximum, after which the distribution becomes chaotic and we lose this Boltzmann distribution. And we can see how this maximum gamma scales very clearly as 1 divided by the square root of the size of the system. If we look at how this temperature scales, we see a similar scaling for beta and with the size of the system. And we also see how this scaling of the temperature allows a Grover-like enhancement of the ground state population. Here, the enhancement is defined of this way. At the beginning, we have the ground state have the same probability amplitude like as any state. So the probability amplitude of the ground state at the beginning is 2 divided by 2 to the n, where n is the number of variables. So at the end, the enhancement is defined as the probability amplitude of the ground state multiplied by 2 to the n. We see this interesting enhancement over random sampling using one layer QAOA. We also saw different approximated trends for other parameters that were the same for different models that we studied. And in particular, we saw that beta has got the same scaling as gamma. So until now, I told you about some empirical evidence and numerical evidence that we saw to say that QAOA is creating this Pseudo-Boltzmann state, these thermal-like states. Now I'm giving you some insight into the analytical derivation of these states. Okay, so we come back to the multilevel interferometer and we can calculate which is the probability amplitude of one AN state, X, when we apply one layer of QAOA. Okay, and this is the full expression. Okay, if we use Sankull identities, we can define the probability amplitude of every AN state as a sum over all AN states of the system, X prime. And the most interesting thing about this expression is that we are relating the probability amplitude of X with a sum over the Hamming distances between X and every AN state X prime, and the energy of that AN state X prime. Okay? So we are relating these two quantities. We would like to know what is the relation between these two quantities, because that relation will depend on the structure of the spin model that we are optimizing. So here we are seeing that the amplitude of the AN states will have some dependence with the structure of the spin model that we are optimizing. In particular, let's say that we have this AN state X, and we have another AN state X prime. If the Hamming distances between them is 2, the energy of that AN state X prime will have some probability of being in some specific part of the energy spectrum. We have a Hamming distances equal to 5, we'll have a different probability of having the energy of X prime in another part of the spectrum. And the same. So what we want is to know what is the relation between these Hamming distances and the energy and these energies. Because if we were able to find this relation, we could approximate this sum with an integral, with a continuum integral over the probability distribution of these Hamming distances and these energies. And that is what we did. We found that this probability distribution of Hamming distances and energies in the spin models, in the Ising spin models that we are studying, can be very well approximated by bivariate Gaussian distributions. So we saw that if we are in not degenerated models such as QAOA, we can define this probability as one bivariate Gaussian distribution. If we are dealing with a degenerate case, such as mass cut, in which we have one symmetry, we can define these distributions with two bivariate Gaussian distributions. And these distributions will depend on a correlation factor that will be dependent on the specific eigenstate x for which we are calculating the amplitude. This is interesting because if we use this probability in the previous expression, we can solve the integral, and we find that we can express the probability amplitude of the eigenstate as this exponential. Actually, we find a lot of terms in the expression, but the only term that will depend on the eigenstate x that we are optimizing is this term with the covariance. So this correlation factor, this covariance, encapsulates all dependence in x, encapsulates all the dependence in the distribution. That is what we want to see. What is the distribution with x? So we can define of this way the probability amplitude, regardless if we are dealing with a non-degenerate model or a degenerate model. But here we have an exponential of the covariance matrix. We don't have the energy, what is we want to find, because we want to reproduce these Boltzmann states. But again, we can look at the spin models that we are optimizing, and we see that there is a very clear relation, linear relation between this covariance and the energy of the state that we are optimizing, up to some random perturbations that are the same perturbation that we find later in the Boltzmann distribution. So we find a linear relation between the covariance and the energy. And if we substitute this relation in the previous expression, we find that the probability amplitude can be described by these Pseudo-Boltzmann states that we have seen in our numerical experiments, up to some random perturbations. And we can give a closed expression for the effective temperature that depends on the specific correlations of the spin model and the QAOA angle gamma. So having this expression, it's interesting to look at the dynamic of the distribution as we increase gamma. And we see how we get this accurate Boltzmann distribution when we are in a regime with a small gamma. But we see that how when we reach the optimal gamma, we lose this distribution. The distribution becomes more chaotic, and the noise is higher, and we lose this Boltzmann distribution that we observed. And it's the same for degenerate and non-degenerate models. In particular, I would also like to highlight that the expression that we are giving for beta explains this behavior of beta, and at the small gamma regime, this linear relation between beta and gamma. And this is all I wanted to tell you from the physical point of view, from the physics of these QAOA states. Now let's see at the states from the computational point of view. And from this point of view, what we wonder is, could we sample these temperatures with other algorithms, other classical algorithms, such as Markov-chain Monte Carlo algorithms? So we tested it in specific the certain Kilpatrick model, and we use what is, to the best of my knowledge, the state-of-the-art threshold to these models. This threshold says that Markov-chain Monte Carlo algorithms can sample in polynomial time any thermal distribution of Ising models which have a temperature under this threshold, so have a beta under this threshold, so have a temperature higher than this threshold, and this threshold is given by this expression and is given in this reference. This expression depends on the norm of the interaction matrix J. So what we want to do is to compare the temperatures that the approximated temperatures that we are getting with QAOA and with this threshold to the Markov-chain Monte Carlo algorithms. And what we see is that the inverse temperature of QAOA states surpasses this threshold by a distance that remains steady when we increase the size of the system. Here, the orange line is the classical threshold, and the black line is the QAOA average. And every points are different random distances that we are optimizing. Of course, this is just a theoretical threshold, so practical realizations of these algorithms may surpass this threshold, but it's a proof of how good are the temperatures that we are getting with only one layer of the QAOA. And it's all I wanted to tell you about our work, just to give you a brief, to give you a summary of all the work. We used a new theoretical approach to reveal that QAOA, that the one layer QAOA is creating thermal-like states. We explained this behavior with hidden correlations in the spin models that we are optimizing. And regarding future work, we think that this work will help to give a better understanding of multilayer QAOA and adiabatic quantum computations. We have been working on it, and I think that we will publish some work on it very soon on arXiv. And we think that one may relate a full adiabatic protocol to a process that creates these Pseudo-Boltzmann states. That would be very interesting. And we think that this study gives an insight on the nature of the states that are created through imperfect adiabatic evolution. So, well, thank you very much. Let me acknowledge to my group. We are based in Madrid. We are QINFOG. And, well, they are my collaborators, my supervisors, J.J.García-Ripoll and D.Porras, and a collaborator, Fernando, who right now is at the University of Valladolid in Spain, at myself. Well, thank you very much for your attentions. I'm available to answer any question right now or by email at any time. Thank you very much.
Thank you, Pablo. So it's already 30 minutes, but we have a couple of questions. Okay, do you have any questions? Okay,
Pablo, sorry, I was having difficulty unmuting. I apologize. I have a question. Thank you very much, Pablo. Very nice presentation. So I guess your numerical stuff, as you said, where you get these nice quasi-Boltzmann distribution, were all done on a single layer. And then you said at the end you started to do multiple layer. Can you give us a suggestion of what happens when you go to many more layers? Do they become less thermal? Do they condense more to the ground state? So what happens?
Yeah, that's a very interesting question. Yes, well, I think that, well, as I said, I think that we will publish some work on it very soon. Okay, so that what we are seeing is that if we are optimizing the angles with optimal angles, we are losing this Boltzmann distribution. We are watching some kind of Boltzmann distribution because we are watching a lot of noise, that the noise increase. But we saw that we can recover some approximated Boltzmann distributions with better temperature when we increase the layers. So we see that if we are optimizing the angles as we are doing here, we are not watching a so clear Boltzmann distribution because the noise is higher. But we can get with different angles good Boltzmann distributions at different temperatures. I think there is another work that is studying these approximated Boltzmann distributions with multi-layers that is already on arXiv. And they explains that even though those distributions perhaps are not so clear like these ones, if you measure some entropies and some specific quantities, you get good approximative results for those distributions.
But
So
I guess as p infinity, you must eventually end up at t equals 0, or beta is infinite. So presumably there's an optimum number of layers, or am I overinterpreting this? Is there likely to be an optimum number of layers that you need to run on QAOA to give you the most Boltzmann-like distribution?
Exactly. That's the point. If you want to reach a specific Boltzmann distribution with a specific temperature, you have to increase the number of layers until some point. But if you are just using a specific number of layers and you are optimizing the angles to reduce the expectation value of the Hamiltonian, and you watch which is the Boltzmann distribution that you are getting, as we are doing here, because here we are not fixing the temperature, we are just watching which is the temperature that we are getting when we are optimizing. In that case, you obtain a distribution that has more noise, that is not so Boltzmann. But of course, you have some available temperatures under, and that will give you some good Boltzmann distribution with that specific number of layers.
Okay, so let's see. Fine. Good, thank you. Very interesting.
Any other questions? Okay. Thank you again, Pablo.
Okay, thank you very much.